Hi, this video talks about Ampere's law and how we can use it to find the magnetic fields of very highly symmetric situations. And Ampere's law, in terms of ideas that we've seen before in class, is probably closest to Gauss's law. Now, Gauss's law talked about how we could determine electric fields, in part, by taking a look at a property that we called the electric flux, which is how a field goes through a surface. And what Gauss said was, with electric flux, if we calculate the total electric flux through a closed volume, so that circle on the integrand side means closed integral of the electric field dotted with the element of area dA, the total electric flux through any closed surface has to be the charge inside divided by epsilon naught. Similarly, Ampere's law talks about an imaginary or virtual geometric shape. Only instead of talking about volumes, we talk about paths. And the path that we'll talk about is what we call an Amperean loop. And what Ampere's law says is we could take a look at the circulation of the magnetic field. And the way you calculate circulation is you take the integral of a field acting along some path. And along a closed path integral, the total magnetic circulation, the integral of the magnetic field acting along that closed path, is going to equal mu naught times the current enclosed by the surface created by the path of your Amperean loop. So in this picture, the area would be everything inside the dashed black circle. So any current, so here I have a wire with a current, that little dot means it's coming out of the board. So whatever current that wire's carrying, that's contributing my magnetic circulation. And again, mu naught is the permeability of free space. 4 pi times 10 to the minus 7 Tesla meters per amp. Now, if we wanted to use that for figuring out the magnetic field, like Gauss's law, it means we need to rely on either symmetry or rely on the dot product bailing us out of some tricky situations. So in highly symmetric cases, often we're going to be able to argue that the magnetic field would have to be uniform. And if the magnetic field's uniform, it can come out of our integral, and the integral along our path is just going to be the length of our path. So a classic example of this is looking at the magnetic field of a wire, but inside the wire as well as outside. Now with the Biot-Savart law, it's not too bad to try and calculate the magnetic field of an infinitely long wire. But it doesn't really work if we want to look at what's happening inside. And it turns out, inside that conductor are magnetic fields. So what we can do is we can take this problem and break it into two regions. Outside the wire and inside the wire. And outside the wire is easier, so I'll talk about that first. Now, to make my Amperean loop, I'm going to choose a circle that is radially symmetric, centered at the center of my wire. Now, if I make this wire infinitely long, the magnetic field should be uniform at all points along this Amperean loop. So with a uniform magnetic field, my circulation would be my magnetic field times the circumference of my circle, 2 pi times the radius. And that would just be equal to, according to Ampere's law, mu naught times the current enclosed. I'm outside the wire, so my current enclosed is my total current I. So the magnetic field outside is the result that we get from the Biot-Savart law, mu naught I divided by 2 pi r. Inside, though, we need to think about the current density. And as we said when we first talked about current density is the total current divided by the cross-section. So if we have a circular wire, the cross-section would be pi times the radius of the wire, which I called A squared. So my Amperean loop is again going to be circularly symmetric, centered around the center of the wire, and again, because of that circular symmetry, I should have a uniform magnetic field So my circulation is still the magnetic field times 2 pi times the radius. Now, the enclosed current is going to change as my Amperian loop grows. Any current outside my Amperian loop doesn't count. Any current inside the Amperian loop counts. So my current enclosed is going to be my current density times the area of the surface bounded by my Amperian loop, which would be pi times the radius of my loop squared. Well, the pi in the area of my Amperian loop and the pi in the cross-section of my wire cancel out. Well, if I set my enclosed current, plug it into this top equation, I have a radius that shows up on both sides of the equation. So that factor of the radius cancels out. And what we're left with is a magnetic field that depends on radius, but instead of being 1 over the radius, it's going to go like the radius. It increases linearly. Just like with gravity, the gravity inside an object of mass increases linearly if it's a uniform object. Inside a charge, the electric field increases linearly as we go through that charge that has a uniform charge density. So with a uniform current density, the magnetic field that we see inside a wire would be mu naught times the current of the wire in total times the radius of our Amperian loop, which is our radial distance away from the exact center of the wire, divided by 2 pi times the outer radius of that wire squared. So when we get the radius equal to the radius of our wire, we get the exact same result. That drops off like 1 over r as we move forward. Thank you for watching.